The next step in our derivation is considering how we actually apply this relationship between unit stream power and erosion and how we obtain the right terms. The first piece to consider, and probably the obvious one, is to relate this erosion rate and this constant right here to real measurable parameters by expanding this stream power term. So we have rho g q over channel width b, with q discharge, s the slope, and rho is the density, g is acceleration due to gravity. So expanding this out into some of its, real terms that might mean something in the real world. And so from here, we actually already have everything that we need to do this if we can go out and measure variables in the field. So we can apply if discharge, width, and slope are measured. And there's a little happy face about that. However, that's sometimes not good enough for us, and here's why. So as geomorphologists, we often work to understand landscapes over longer timescales than we can really measure. And in particular, when considering bedrock erosion, we're often concerned with timescales of mountain belt growth information. So let's say million to millions of years. And we might also want to analyze topography in the landscape with this topography forming over hundreds of thousands to millions of years, and use analyses of topography to directly connect our observations to erosion rates. And this is sort of similar to what we've discussed earlier on this semester with hill slopes and hill slope diffusion. And if you're some poor soul watching this lecture without taking part in the class in the same order, just completely ignore that comment. So this erosion rate, therefore, might more conveniently be related to something that we can pull out directly from a map instead of needing to go out and make field measurements. Well, good news is that we can directly get channel slope from digital elevation models. At the time of initial development of the stream power law, we couldn't really get width very easily, but now we have such high resolution imagery we probably can. But we still often don't. It still isn't quite such a common practice here in the year 2020. So I'm going to go through the methods that we use in general that have been passed down through the decades. And then Q, which is discharge. This is the difficult one, because this varies a lot in time, this varies rapidly in time, and we have to figure out what is this important dominant discharge, in other words, what's the geomorphically effective discharge that's causing the channel to evolve. And so sometimes it's actually easier to create some sort of scaling relationship. And that's what I'm going to draw down here. So what we might want to do then is convert the discharge into something that we can measure easily from a digital elevation model. And I'm going to say that we want to convert discharge into some function of drainage basin area. And why is that? Well, it's because if I have a drainage basin, I'm going to draw this in green on the ground, like so, that has some stream channels, carving through it, flowing, coming together, and so forth. What I might have up in the sky is a little puffy cloud like this. That is not my favorite cloud. Yeah, that's not a very good cloud either. All right, take 3. Maybe if I do, oh yeah, there we are. It looks a little like a loaf of French bread, but you get the idea. Let's just label it cloud. Yeah, it's not cloudy with a chance of baguettes today. So, and this cloud is going to be precipitating in some way on the watershed. So we might have rain, we might have some snow, who knows? Might have some wintry mix for those of you guys from Boston or Toronto. Don't you love that stuff? So, in any case, have a cloud it's precipitating on the watershed, and therefore we might just say that there is going to be some sort of generic relationship where the discharge Q out of the watershed could be related to the precipitation P going into the watershed. And typically in a watershed, we might consider also evapotranspiration as a source of losses. But if we're thinking specifically of storm flow, so we have a big storm on a watershed, and a watershed that might not be so large that it takes forever and a day for the water to get from the clouds all the way to the discharge point, this Q. And not necessarily those exact water molecules. There might be some exchange with groundwater. But if we ignore the complexities of the hydrological system, which I'm having a hard time doing as I'm just discussing this right now, we might be able to say that there is a simple relationship in which the discharge is going to be equal to some coefficient, so some K converting area to discharge term, times drainage basin area to some power P AQ. And so this is just a simple power law approximation. And it is totally empirical, meaning that it's just we come up with it from measurements and not at all with theory. And from using measurements to get this, we generally get that this relationship holds with an exponent. PAQ is approximately maybe 0.6 or so to 1.0. You might see 0.7 to 1. You might see sometimes 0.5 to like 1.1. Occasionally this can be greater than 1 depending on the relationship between these storms and groundwater. But if it's 1.0 right here, then what you know is that you basically just have a relationship in which, I'm going to go back to black. If this power is 1.0, then you know right here that you just have discharge is equal to the precipitation rate times the drainage basin area. And so this is going to be, KAQ term is going to be a strong function of precipitation rate. That's P. And it's also going to be a function of this power term right there. And so here P stands for power, here P stands for precipitation. I apologize, we really just need language with more letters. I mean, we already took all the ones from the Greeks, right? But we still don't have enough for science. So with that, then actually I'm going to scroll up just a little bit so we can see this equation. So if we take this equation right here and we plug in this form like this into our unit stream power to erosion equation. So we started out with erosion rate is equal to K suberodibility times rho G Q over B times slope. And now we're substituting in for Q. And so this is going to then be equal to K suberodibility. And then I'm going to add this K AQ. So this is converting drainage basin area to river discharge, like I said, times rho G A to the P AQ over with times channel slope. All right, and so then just so we can have these things written down in more than one place, this is function of erodibility and sediment as tools or cover. So tools for erosion or covering the bed. And this term right here is going to be a function of the precipitation rate associated with the geomorphically affected flood, and then also of this power PAQ, because there's going to be in this power law equation some trade-off where, let's say, if this exponent here gets higher, maybe this has to get lower in order to fit the data properly. And so that's just really an empirical relationship right there. So not meaningful in any major theoretical way, but important for being able to get the equation to fit the data. All right, the next term that we want to deal with is channel width, because even if we now have satellite imagery, channel widths can change dramatically with time, and they change as the hydrology and discharge changes as well. So the channel width that you measure today might not be the channel width that we had, 6,000 years ago during the mid-Holocene climatic optimum when we had bigger storms, in the same way that we're kind of looking towards into the future with ongoing climate change. It might look very different from what we had 26,000 years ago when we were entering the last glacial maximum. So if we wanted to think about kind of how to make a more generic relationship between these different terms, then we might want to think more about some kind of relationship that links channel width with something else that we know. And as a matter of fact, so Woolman and Miller came up with, in an article that they wrote, and these are a couple eminent geomorphologists. Reds Woolman just passed away a couple of years ago. John Miller, unfortunately, passed away quite young. But so from these two guys, we know that the width of a channel is proportional to the discharge to the 1/2 power. And so this proportionality term, we can also just replace this with a constant. So I'm just going to say B is going to be equal to some K QB. So this means a coefficient to convert discharge into width times river discharge to the 1/2 power. Okay, now let's just plug that into our stream power equation as well. And we get erosion rate is equal to K epsilon times K AQ. And then we have KQB. That's going to go in the denominator since width is down there. So KQB. Then we have Q to the 1/2 on the bottom, and we have area to the PAQ on the top. And I think you might be able to see where we're going with this. And before I do that, almost forgetting density and gravity, those constants, I was getting away from me. So area to the PAQ over Q to the 1/2 times slope. And now, of course, we're going to want to replace this Q term again, this discharge term again. And so what we're going to do is just remind ourselves that Q is equal to KAQ, Q to the PAQ. And so if we have this here and all this in the denominator, then we have this whole thing raised to the 1/2 power, right? So Q to the 1/2 is going to be equal to this whole thing to the 1/2 power, which means that Q to the 1/2 is going to be equal to KAQ to the 1/2 times Q to the PAQ over 2. So we can apply the PAQ here and the KAQ over here and say that erosion rate then is going to be equal to our erodibility coefficient times this drainage area to discharge coefficient that's related to precipitation and to the exponent in the relationship, KAQ to the 1/2 power, and that's because we then divide it by KAQ to the 1/2 from this denominator term. And then we're going to keep this all over KQB, this coefficient relating channel width and discharge, times density, times acceleration due to gravity, and then this whole thing multiplied through by drainage area in the numerator, divided by, I made a mistake over here. So what I really should have written here instead of Q is A. Let me just erase that right now. Oh. So hopefully you caught that as I was going through this, but if you didn't, I'm just going to go back for a moment. So here we have discharge, relaying that discharge to drainage basin area, hence I have these powers PAQ on these terms. So then we have a to the PAQ over here, and then we have a over a to the PAQ over 2. So now we're just going to have a to this power AQ over 2 times slope. Well, folks, we are just about at the finale, because what we now have is this equation, this right here, where these first terms, let's just lump all of these terms into one big constant called K. So now erosion rate is equal to K. And then we have a to the PAQ over 2. And not knowing exactly what this power is, let's just call it m. So we're going to lump that all together. And then we have slope. And at the very beginning, I posited that this was a linear relationship between erosion rate and stream power. But let's imagine that maybe it's not. Well, if it's not a linear relationship, then this term already has a power here, and this term already is a constant, so that's just going to absorb the power and become a new constant. So we're just going to add a coefficient up here, which is just like in case of nonlinearity. So this is the most general form that we use and apply very often of the stream power equation, where we have erosion rate is equal to K, this coefficient, times a to the m times s to the n. And that one is getting a box and a big arrow, because this is the stream power law. And one form of the stream power law that's used very commonly is the form in which we just assume that there's a linear relationship between drainage basin area and discharge. So every raindrop that hits the drainage basin goes to the outlet, and every storm completely covers the drainage basin, so that we have this nice snappy linear relationship between those two. And so that means that PAQ equals 1. So if Q is just equal to precipitation times drainage basin area, then PAQ equals 1. And let's also just assume linearity. Erosion rate, as we stated initially, is just going to be proportional to, if I can actually write proportional to, oh goodness, I'm in the lower right corner of the tablet with my hand half hanging off. I think that's the problem. So erosion rate is just linearly proportional to omega. And so that means that we would have n become 1. So if we do that, then m equals 1 from the PAQ over 2, which comes up from the inclusion of channel width, and n equals 1. Interestingly, this set of coefficients implies that there's a self-similarity or a scale independence, so we're actually going to see the exact same features at different scales. So we'd actually see we'd be able to directly look at a landscape that's 1,000 kilometers wide and one that's 10 kilometers wide, and for some tweaking some parameters like K, we might not actually notice any kind of difference. So that is a little weird. It's kind of a funny result. But in any case, this is a common assumption for what these parameters are. Oftentimes, m, because of this precipitation and drainage basin area relationship, can be taken sometimes as a bit smaller. So we can say often 0.35 to 0.5 or so. No hard and fast rule. But if we take these guys over here as this is, one common way in which this is written is E equals K, A to the 1/2, S to the 1. And one nice thing about that is that then area to the 1/2 has units of length. So we can just say that this is going to be in units of meters. S, slope, obviously has no units. Erosion rate is in units of length per time. So let's say meters per year. So we're going to escape SI units for a second because erosion in bedrock is usually pretty small and it's just hard to visualize values that are that small. And so therefore, this is going to have units of 1 per year. And so then therefore becomes a very easy to understand rate constant. So it's similar to similar units to like an exponential decay constant or something. So we have the area, which is telling us how much length is going to be eroded, which relates to how much water is going through the channel. And we have this K term, which tells us how fast, so how efficiently this water is being converted into erosion, which we can then take conceptually all the way back to considering stream power and how much of that potential energy is being effectively converted into kinetic energy via how much mechanical energy is required to break down the rock and remove material. And so this is the stream power law, and the main one that's boxed right here is the one that's going to be used consistently and that you're going to want to remember for working in geomorphology and landscape evolution.